In the last video, we went through the criteria referred to as Huckel's rules, which determine whether a molecule is classified as aromatic, meaning extremely stable, anti-aromatic, meaning extremely unstable or less stable than would be anticipated for a comparable conjugated molecule, or whether the molecule is neither aromatic nor anti-aromatic. In this video, what we are going to do is walk through a few example problems to make sure that we are all on the same page about identifying molecules or classifying them as aromatic, anti-aromatic, or neither. As a reminder, I've posted Huckel's rules here in our upper left corner for a reminder of our last video, where we say a compound will be aromatic or anti-aromatic if the molecule is cyclic, if the atoms in the ring are planar, which generally denotes that the atoms of the ring can adopt an sp2 trigonal planar hybridization state, and then finally, to dissect whether the molecule you're looking at will be aromatic versus anti-aromatic, it's aromatic if the number of electrons in that ring that occupy 2p orbitals is equal to 4n plus 2, where n is any integer. So imagine we filled in n as 1. 4 times 1 plus 2 is equal to 6. So if we count 6 electrons in that ring, that is going to mean that the molecule is aromatic. The compound, on the other hand, is anti-aromatic and extremely unstable if the number of those 2p pi electrons is equal to 4n, where n is any integer. So hence, if n is equal to 1, 4 times 1 equals 4. So it'll be anti-aromatic if there are a total of 4 electrons in those 2p orbitals of the ring. So taking a look at the two structures that we have here as our examples, and as always, I encourage you to hit pause, try to solve these on your own using the rules that we just went over here, and then determine whether you got it right by hitting play or not. So let's take a look at the solutions to this. So in the top right corner, we see that we have a carb anion, because we have that negative formal charge there. And we have to first ask, is the molecule cyclic? Yes, it is. Is the molecule planar, meaning that all the atoms can adopt an sp2 hybridization? So as it's written right now, that carbon that is the anion right here would actually be sp3 because it has the hydrogen that we aren't showing that's implied, 2 bonds to other carbons, plus the lone pair of electrons that's necessary to make that negative formal charge. So we'd have 4 regions of electron density and it has to be sp3. So we have to ask first, can we draw a resonance structure that would allow that set of lone pair electrons to become a pi bond? And so we need to make sure that we can actually do that. If we took this lone pair of electrons over to here, we could then take the pi electrons from there onto this carbon right here. And indeed, this will allow us to show that those lone pair electrons, by resonance, can become part of a pi bond. And so therefore, yes, indeed, all of the atoms in at least one resonance structure can be sp2, because we have an sp3 carbon right here at the top in the right-hand structure that becomes sp2 over here. We had an sp2 carbon right here on the right-hand structure that I'm highlighting that becomes sp3 over on the left, and that's fine. It's just that when we look at the total of all the resonance structures, we have to see that in at least one resonance structure, this particular atom that I'm circling has to be sp2 in at least one of the resonance structures, and that's definitely true over here. So we're good to go on that. And then counting our number of electrons to meet this criteria for aromatic, anti-aromatic. So looking at our structure, whenever we have pi bonds that are within the ring, those are going to each contribute 2 electrons toward this count of 2p electrons or pi electrons. So we're going to count 2 electrons for that pi bond, 2 electrons for the other pi bond, and then whenever we have a set of lone pair electrons that can participate in resonance to become a pi bond, we count those as well. And so therefore, this set of lone pair electrons is going to count as 2 electrons, because both of those 2 electrons we can show by resonance will participate in formation of this pi bond here. So that's a grand total of 6 pi electrons. And so then we have to ask, which of our templates does the number 6 fit? Does it fit the criteria for aromaticity, meaning 4n plus 2, where n is any integer, is equal to 6, or 4n is equal to 6. So if we set 4n plus 2 is equal to 6, n, we could solve for using algebra as being equal to 1. Since 1 is an integer, that means that this 4n plus 2 rule works out, so the compound is aromatic. And so therefore, I'm going to label our top structure here as aromatic. What it means to say that this structure is aromatic is that this carb anion is much, much, much more stable and favorable to form than a typical carb anion. Carb anions are generally pretty unstable reaction intermediates. And relative to those unstable reaction intermediates, this one is remarkably stable. Granted, it's still, since it has that negatively charged carbon, not the most stable molecule in the world, but compared to a typical carb anion, it's much lower in energy and much more stable than we would anticipate. And that's due to the fact that this structure is aromatic. So what about our carbocation alternative down here on the bottom right? So thinking about it in terms of its aromaticity or anti-aromaticity, we go through the first couple of rules. Cyclic, planar, all atoms can be sp2, and that is indeed going to be the case without even drawing any additional resonance structures here, because that carbocation has 3 regions of electron density, so that means it's sp2. And then looking at whether the structure is aromatic or anti-aromatic, counting the number of 2p electrons, so we have a pair of electrons right here, pair of electrons right here, those pi bonds are always going to count. And then at our carbon up here, we have no lone pairs and no pi bonds, so there's nothing to count there. So even though it's an sp2 carbon, it's not contributing anything toward this count. So we just leave that as 0. There will be no electrons to count in the 2p orbital there. But since it's sp2, we can still continue on with thinking about it being aromatic or anti-aromatic. So in total here, for this particular structure, the grand total number of electrons toward that 2p count is going to be 4, because there are a grand total of 4 electrons in those 2 pi bonds that are present in the molecule. And the carbocation doesn't contribute any electrons additionally to that count. So 4 electrons, we match up with either the criteria for being aromatic or anti-aromatic using the formulas here, where if we take 4n, that's the criteria for being aromatic, and set it equal to 4, n will solve by algebra to be equal to 1, which is an integer, meaning that the structure is anti-aromatic. And any molecule that has 4 electrons in those 2p orbitals is going to be anti-aromatic. So therefore, this compound is indeed anti-aromatic. Let's erase this and take a look at another couple of examples here to make sure that we've looked at a variety of different scenarios where you can apply Huckel's rules of aromaticity and anti-aromaticity. So let's go ahead and take a look at these 2 new example problems here and here. We'll start with the one up top here. And you'll notice this one may initially throw you a little bit off because it is a bicyclic system. We have the 2 rings that are fused here. When you have 2 fused rings, you can consider the ring system as a whole, going around the entire large ring system. That's that compilation of 2 rings, if possible. If you can find a conjugated network or a network where you can form those sp2 hybridized orbitals all the way around, then you're going to use that largest possible network as your determinant of how many of the 2p electrons there are for the aromatic versus anti-aromatic description. So you're looking all the way around the ring to see if you can form a complete network of sp2 hybridized atoms to create this aromaticity or anti-aromaticity. So let's go around and take a look at this structure and determine whether there's a way to make all of the atoms sp2 all the way around. So taking a look, we'll just start here at the carbonyl up top. That carbon's already sp2, so we don't need to do anything there or think about that any further. Next carbon, already sp2, so we don't need to do anything there. Our next atom in the ring, this nitrogen. That nitrogen has a lone pair of electrons on it. Since it doesn't have a formal charge, it has to have a lone pair there. And that means that nitrogen is going to be sp3 because it has a total of 4 regions of electron density with the 3 covalent bonds and 1 lone pair. So we will have to deal with that eventually and see if we can make that sp2. I'm going to go around the ring to this carbon is sp2 already. Nitrogen right here has a lone pair of electrons. That particular nitrogen is sp2 because there's 1, 2, 3 regions of electron density with the pi bond, carbon, the carbon-carbon single bond, and the lone pair. That's 3 regions, so that's sp2. This carbon right here is sp2. Nitrogen right here has the same situation that we did at the nitrogen in the upper right corner right here, that this nitrogen is sp3 as it's written right now. So we will have to deal with that one a little bit later. I'll put a highlighter on that and a highlighter on the other sp3 nitrogen to remind myself that we need to make sure we can make those sp2 by resonance. sp2 carbon right here at the carbonyl. And then finally, this nitrogen right here would be sp3 based on the way that it is drawn right now. So we either need to draw out or mentally confirm that each of the 3 nitrogens that I've highlighted that are currently sp2 could be sp3 by resonance. And it is the case that all 3 of those could be sp2 by resonance. I'm not going to draw out every single one of them, but I will illustrate that, for example, we could take the nitrogen atom lone pairs and bring them over to here using the red electron pushing arrow. And then that pi bond has to go somewhere. One possibility would be that it could come up to here to make a carbon-carbon double bond. The bond to the oxygen could come, the pi bond to the oxygen could come up onto the oxygen, and that would create a resonance structure here that would illustrate to us that there is a nitrogen-carbon double bond there in one of the resonance structures, and that as a result, that nitrogen could be sp2 hybridized in some scenario in one of the resonance structures that we can draw here. And so I'm not going to do that for every single one of these 3 nitrogen atoms that we have around the ring that are sp3 in our original structure, but you should be able to recognize that you could draw resonance structures in each case that would allow you to show that that nitrogen atom is able to use its lone pair electrons to participate in resonance and as a result become sp2 hybridized. So it does fit that criteria that all the atoms can be sp2 hybridized. So now that we have confirmed that, we need to go in and take a look at counting the number of 2p electrons that will contribute toward aromaticity or anti-aromaticity. I'm going to erase these electron pushing arrows and things just to clean up the structure a bit so we can take a closer look. So let's go around the ring and count the number of electrons will contribute toward those 2p orbitals and determine whether the molecule is aromatic or anti-aromatic. So going around the ring, looking at the nitrogen atoms with their lone pair of electrons, each of those nitrogens with a lone pair that were originally sp3, all the ones I've highlighted in pink, will all contribute their lone pair electrons toward that pi count because we were able to show by resonance, for example, with this nitrogen right here, that we could take that lone pair of electrons and convert it into a pi bond. So all 3 of those sets of lone pair electrons will count for 2 apiece. So that's 2, 4, 6 electrons from the nitrogen atoms there alone. What about the nitrogen atom over here? This nitrogen atom also has a lone pair of electrons, but it also has a double bond there. So it's got a double bond and a lone pair. In the case of this, when we have a double bond and a lone pair of electrons, only one or the other can count because they can't both occupy that single 2p orbital that is associated with the atom here. And so as a result, count one or the other, not both. I'm going to count just the double bond here. So the nitrogen carbon double bond right here would count toward our 2p number there. So that would be 2 additional electrons there. And again, we are not counting this set of lone pair electrons because it's associated with an atom that's part of a double bond. And due to the fact that there would be 2 sets of electrons here, the pi electrons of the double bond and then the electrons from that nitrogen, they can't both be occupying that vertical 2p orbital. So count one or the other whenever you have a lone pair and a double bond at the same atom. So that's 2 electrons there. Continuing around the system, we come to here and we have a carbon atom here and here to consider. Both of those are sp2 carbons as they need to be for this system to work out. And both of those electrons of that pi bond will count toward the Huckel number because of the fact that those 2 pi electrons that are currently kind of bridging the 2 rings, we could show those 2 pi electrons by resonance as being part of this large ring system in general. And in fact, that's what we did down here in this second resonance structures. We had moved those pi electrons up to here so that they are part of that full ring network, where we describe the full ring network as this whole big entire ring there, rather than a ring that's cut off halfway through. So these 2 do count because of the fact that by resonance you could show them coming up to here to make a carbon-carbon double bond that is part of that large ring network. We come to the carbon right here. Don't count any pi electrons here because those 2 pi electrons that go up out of the ring toward the oxygen, there's no way to reasonably make a stable resonance structure by moving those 2 pi electrons down into the ring. And so therefore, since these 2 pi electrons are external to the ring, don't count them. The carbon is just hanging out there as an sp2 carbon. Nitrogen, we counted those 2 electrons already by highlighting them because we recognized they could, by resonance, participate in this ring system of conjugation. Coming over to the carbonyl group right here, that carbonyl group carbon is sp2, so it's able to participate in this aromatic system, but we don't count those 2 electrons from the pi bond because there's no way for those 2 electrons to be part of the resonance system to make a stable resonance structure by moving the pi electrons from the carbon-oxygen bond into the ring just is not going to work. So leave that untouched. So going around and counting all of our highlighted pink electron pairs here, I see that we have a grand total of 6 electrons corresponding to 3 nitrogens, which each bring in 2. Plus we have 2 pi bonds we've counted. So that would be 6 plus 4 makes 10 electrons in total as our count of 2p electrons. And so therefore, in thinking about what paradigm this fits, aromatic versus anti-aromatic, this is going to fit the schematic of being aromatic, because if we were to take this 4n plus 2 equation and fill in n as being equal to 2, we had a 4 times 2, which makes 8, plus 2 makes 10, and 10 is the number of electrons that we have there. So this compound is aromatic. And in fact, what I didn't tell you at the beginning was that this compound is a very common compound referred to as caffeine. And caffeine, of course, it's quite stable because we're able to heat it up when we brew coffee, and the molecule remains intact and ingestible and gives us all of those nice stimulant type effects that people tend to really like. So that is the structure of caffeine, which is indeed an example of an aromatic compound. So now we'll move this compound front and center here. And this particular compound, we need to take a look at and assign as aromatic, anti-aromatic, or neither. Going through our criteria, it is cyclic, check. It is planar because all the atoms can be sp2, and in fact, right now, all of the atoms are already sp2 without doing any additional resonance structure, so that's cool. And then to determine whether it's aromatic or anti-aromatic, we count the number of electrons that occupy those 2p orbitals. So how many electrons occupy those 2p orbitals? Well, let's take a count. So our carbon-carbon double bonds or carbon-nitrogen double bonds within the ring are always going to count. So we count all those pi bonds within the ring. So pi bond here, pi bond here, pi bond here, all of those count. So that is a total of 6 so far. And then with regard to the nitrogens, keep in mind each of these nitrogens has a set of lone pair electrons on it. But those lone pair electrons are not going to count toward the aromaticity because of the fact that we already have a pi bond right here. So it's not possible for that lone pair of electrons from nitrogen to come in and occupy that same 2p vertical orbital as the electrons from this nitrogen atom. And so those nitrogen electrons do not count, and that's true anytime you have a heteroatom or atom that has a lone pair of electrons and it's bonded to a double bond. Those are not going to count toward aromaticity. So in total, we have 6 electrons that count toward that 2p or pi electron count. And 6 is indeed one of our aromatic Huckel numbers. And so we would declare this molecule is aromatic. So now that we've gone through this set of example problems for applying Huckel's rules, you should, on your own, through the worksheet and the upcoming quiz, be able to look at representative molecules and establish, by following the rules here, whether those compounds are classified as aromatic, anti-aromatic, or neither. And you should also be able to assign how many electrons fit into this definition of determining aromaticity by counting the number of 2p or pi electrons that are found within these cyclic systems.